Hello class, today we are going to identify differences between cis and trans isomers. We will also assign E and Z configurations to alkene isomers. There's a guided notes worksheet that goes along with this assignment, and at the end of that worksheet there are additional practice problems on cis, trans, and EZ isomers. We've previously talked about isomers. Isomers have the same molecular formula but different structures. So they have the same number of carbons, hydrogens, oxygens, etc. But the way they're attached is different. So we've previously looked at constitutional isomers. These are things that, again, have the same formula, but maybe the type of substituent that is attached to the molecule is different, or the position of the substituent is different, or even the parent chain is different altogether. But the key is they still have the same formula. So constitutional isomers are very different compounds from each other. When we're looking at stereoisomers, these things are more closely related, but the point of attachment in three-dimensional space is different, and as a result, that affects the physical properties of the molecules that we'll see. One group that this falls under is the cis and trans isomers, or E and Z isomers. That's what we're looking at today. And in a future lesson, we'll look at chirality, and that will help us explain isomers that contain asymmetric centers. Again, because this can affect physical properties, this will have really important applications for things like medicine and different conformations of drugs and things like that. So cis-trans isomers, cis and trans specifically refer to the position of the substituents either on a ring or a double bond. If it is a cis molecule, the substituents are going to be on the same side of the ring or the same side of the double bond. If they're trans molecules, the substituents will be on opposite sides of the ring or the double bond. The reason we need to distinguish this is because cis and trans isomers result from restricted rotation. What that means is that the substituents themselves are locked in position and do not have the ability to move. As a result, that creates different molecules. So when we look at rings or cyclic structures, these can restrict rotation, and as a result, the substituents end up locked in their positions. You would physically have to break the ring in order to move these substituents around. They cannot interconvert easily. So one thing we need to talk about, just as a reminder, we have our wedge and our dashes. So with the wedge that is pointing towards you, if you imagine the molecule as a flat molecule, even though we know it's not flat, a wedge indicates something that is pointing towards you out of the plane of the paper, and a dash is away from you. So if we're looking at our cis molecules, you'll notice that both of these have dashes, so both of our substituents are pointing towards us, which means they must be on the same side of the ring. If you've got a wedge and a dash on a ring, one is pointing towards us, one is pointing away from us, they must be on opposite sides of that ring in order to be depicted that way. Therefore, they have to be a trans molecule. Another example, if I had both dashes, those are both pointing away, but they're still on the same side of the ring, so they would still be considered cis. We're not going to look at cis and trans molecules for cyclic structures very often, but it is good to know in case you come across it in passing. The more important application of cis and trans isomers is dealing with double bonds. Double bonds can also restrict rotation. If there is no double bond present, and you only have sigma bonds, there's free rotation around that sigma bond because the only orbital overlap you have is from an sp3 orbital. So let's say I had something that looked like this. We can do H's, and really there should be a third H here, and then another H there. Sorry, second H, not a third H. Since there's no double bond at this position, we can rotate our molecule and rotate one half of the molecule. If you just held one part in position and then rotated the other part, there's free rotation there. And that's because there's only sp3 orbital overlap. When we're looking at double bonds, we know that we are sp2 hybridized. So in this center position here, you have sp2 overlap. And because it's sp2, that means we have an unhybridized p orbital. And since we have an unhybridized p orbital, we end up with p orbital overlap side to side. And when we have p orbital overlap side to side, that locks the molecule into position, and the substituents attached to those sp2 carbons cannot move. The only way to move them is by breaking the pi bond overlap from the two p orbitals, and then you can interconvert them. So a chemical reaction has to occur in which a double bond is broken in order to get a cis isomer to turn into a trans isomer and vice versa. Notice that we have hydrogens on the same side of the double bond. So if I put a line through the double bond this way, I see H's are on the same side, and then my substituents are on the same side. That would be a cis molecule. If I draw that line through again and I find that the H's or the substituents are on opposite sides of that double bond, then it is a trans molecule. Now, the key with cis and trans is that you can only have cis and trans molecules when there are two substituents. When there's more than two substituents, we're going to use a different naming system or a different categorization system. We'll talk about that briefly. It is important to note, as I stated before, that cis and trans can affect our boiling points and our physical properties. And this really comes into the dipoles that occur between the molecules. When we have a cis molecule, the dipoles do not cancel out, and you end up with a net dipole through your molecule. And as a result, you have stronger intermolecular forces, since you have a dipole-dipole attraction in addition to the London dispersion attractions. When you're looking at a trans isomer, the dipoles go in equal and opposite directions, and so there is no net dipole, so you're left with London dispersion interactions only. As a result, since there are stronger forces in these cis isomers, we end up with stronger or a higher boiling point as a result of those stronger intermolecular attractions. One thing to note is that some alkenes do not have cis or trans isomers, specifically if it's said to be terminal, which means the double bond is at the end of a chain. That means you are going to have two hydrogens on the same side of the double bond. And so as a result, if you have two hydrogens on the same side, and that's what I mean with the same side, these are on the same side of the double bond, then you can't categorize that as cis or trans because we're specifically looking at the placement of the substituents on either side of that p orbital overlap. If they're on the same side of the p orbital overlap, there's no way to distinguish between them. Same thing goes here. These are on the same side, so there's no way to tell. They either have to be both on the same side horizontally or on opposite sides horizontally in order to be cis or trans. If they're on the same sides vertically, it doesn't work the same way. So let's go ahead and try one. This first one, I can draw my line. I see that my substituents seem to be on the same side and my H's are on the same side. Same is a cis molecule. If I go through and do the next one, I see my H's are on opposite sides, and so this must be a trans molecule. Now onto something a little more complicated. When you have more than two unique substituents attached to your CC double bond, the cis-trans notation breaks down and does not work. We have to use a different notation called E and Z. E and Z allows us to categorize based off of priority, and priority will be assigned by atomic number. So if you look here, you'll see I've got 2 unique substituents on this side, plus a third unique substituent here. And the same goes for the other molecule. I have 3 substituents here. So I'm going to have to, use an E and Z system. So in order to assign an E and Z system, we need to look at each half of the double bond. So on the left side, I'm going to compare F, which is directly attached to this carbon, and I'm going to compare the first attachment here, which is a C. So I'm comparing F and C, and I'm going to compare their atomic numbers. So on the periodic table, carbon has an atomic number of 6, and F has an atomic number of 9. The one that is highest gets the highest priority. So I'm going to put a star next to that. Then I'm going to check the other side. At this carbon, I want to look at the first thing attached on each side. I have an N and an H. If I'm comparing N and H has an atomic number of 1, N has an atomic number of 7. 7 is a higher number, and so, as a result, N gets priority over H. You'll notice, based off of the location of the substituents that I starred, that they are on the same side of the double bond. So you would think, oh, this is like a cis molecule. And you would be correct, but we're going to use a different notation. If the top priority groups are on the same side of the double bond, we're going to use Z, which is German for zusammen, which means together. And I apologize if I pronounced the German word incorrectly, but I'm going to try my best on that one. If the top priority groups are on opposite sides of the double bond, like we see here, we're going to use E for entgegen, which means opposite. The way I remember that, there's 2 ways. Someone said E are enemies. E stands for enemies, so they're as far away from each other. They're opposite sides. Or you could say cis is for same, and same sounds like zame, so therefore zusammen or Z. So let's go ahead. We're going to try one. And actually, this first one's pretty challenging. We're going to learn a couple of additional rules as we go. The top double bond here, there's 2 of them. The top double bond I'll refer to as 1, and the one at the bottom here I'll refer to as 2. Now, I'll be honest, the one that is labeled a 2, we're going to look at first, even though we're going out of order. One of the things I mentioned before is that if I am a terminal alkene, meaning I'm at the end of a chain, like this one, I have 2 H's on the same side of my double bond, and then I have another H, and then the rest of my molecule. There's really only one substituent here, and then a bunch of H's. Since there's one substituent, there's no need to classify it as cis or trans, so the second double bond is actually going to be neither. But now we can go through and look at the other ones. So I'm going to cover up half my molecule, and again, here's the carbon I'm trying to identify. So we'll start here and we'll follow it out like a pair of train tracks. So my first position here, I have a C. And my first position here, I also have a C. So what happens when they are the same atom? How do we rank them in priority? Well, we're going to go to the first point of difference. So what that means is I need to look at what's directly attached to that carbon. So this carbon is attached to an oxygen, and then it's also attached to 2 hydrogens. So I'm going to create a list of the elements that's attached. If I'm looking at this carbon, I know it's attached to a C, and another C. It is not attached to any H's. C, C, C. Okay, and again, now I need to just look at the first point of difference. So I see O and C are not the same, so I need to look at atomic numbers. 8 is higher than 6, so the OH side will have a higher priority than the tertiary butyl group side on the bottom. And we're going to use a similar process on this side. So I see my first element in each one is a carbon. So I need to look at what those carbons are attached to. I see that it is attached to a carbon and then again two hydrogens up top. So carbon, hydrogen, hydrogen. If I look at the next one, I see that I have a carbon, but this carbon has a double bond, which is interesting. So the way you have a double bond, when you have a double bond, you need to count that double bond twice. So what we're actually going to do is say carbon, carbon. So you're counting this as two. Count as two C's. And then we'll go back and we know that we're attached to two H's here. So the list is a little bit longer on the bottom side, but this does give us our first point of difference. We see that this is the same, but then we get to here where 6 is going to be greater than 1 in terms of atomic numbers. So this bottom half here ends up with the higher priority. So you have to make your list of elements. All right, if we divide this in half, I see that the stars that I put are on opposite sides. So this molecule will be an E configuration. If the OH and the tertiary butyl group were switched, then it could be a Z configuration, but we'll just have to get some more practice with that, okay? So now what we need to do is name it. So I'm gonna clean this up a little bit. Now remember with naming, we also have a priority with naming. Alcohols have the highest priority, then that's followed by double bonds. So our parent chain has to have both the double bonds and the OH group, and we want the OH to have the lowest number possible. So this ends up with a 6-carbon chain, and we know that 6 carbons is going to be hexane. We also know we're going to have to change that to an ene because of the double bond, but we also have to put in that di prefix because there's 2 of them. So this will be a hexadiene somehow. And then we also know because of the alcohol, we're going to need an OL ending. If we check our second position, this is a tertiary butyl group. Tertiary butyl is tricky because the T does not count for alphabetization, so we're going to use B to alphabetize. I'll just say B to alpha. And then on the third position, we have a propyl group up top. Okay, so first thing I need to do in parentheses is write the position of my double bond that has the E or Z configuration. So I'm going to write 2E and then comma 5. I don't need to write E or Z for the 5. And then I'll have my dash. I've got my 2-T-butyl, 3-propyl. And then I'm going to put the numbers by the ene portion. I could put them next for my double bond, but I'm going to put them by the ene portion because we're also going to need numbers for the OL. Both are correct. If you wanted to say 2,5-hexadiene 1-ol, that is fine. I'm going to write hexa dash 2,5 dash diene dash 1-ol. So this would be the entire correct name, in parentheses 2E, comma 5, 2-T-butyl, 3-propyl, hexa 2,5-diene, 1-ol. And actually, because of the way I wrote it, I don't need a dash in between the propyl and the hexa. The other way you could have written it 2,5-hexadiene, 1-ol. That would have worked as well. I ran out of space there, but you could have done that as the end of your parent chain as well. Okay, one more example. And I'm going to cover up this side of my molecule. I see I have a carbon and a carbon. So I need to look at the first point of attachment and see if there's any difference there. So up top, we're attached to a carbon, and then a hydrogen, CCH. Here we're attached to a carbon and then 2 hydrogens. So based off of the first point of difference, which is here, the isopropyl group up top will have priority. If I go to this other side, it's a little bit easier because there's an H here. So I'm comparing an H to a C. The C is going to have priority. And so if we look at our double bond and assess, I see, here's my dividing line. I see those stars are on opposite sides. This is also going to be an E. So now we just need to label everything. We need the longest parent chain, and we have to have the double bond included. And the double bond has to get the lowest number. So the lowest number possible for that double bond is a 4, and this parent chain is 9. So this is going to be non-ene. When we're ready, we have a substituent, a methyl group on the 2 position, and we have an isopropyl group on the 5th position. And then we know that our double bond is on 4. So in parentheses, we say E, and then we go alphabetical order, 5 isopropyl, 2 methyl, 4 non-ene. And that is our final answer. Now, as a side note, you may be asked later to draw both E and Z isomers for something. So if you have an E isomer like this one thing you can do is look at one half of the double bond and switch the substituents that are attached. If you switch their positions, you will get the opposite configuration, which would be Z. So if I am looking at this one, if I redrew it, and this is the hard part. Actually, let me redraw it down here. If you redrew it, so everything looks the same on the right side of the molecule, but instead I put the isopropyl group pointing down instead, and then 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons here. This would be the Z isomer, because now the 2 highest groups are going to be on the same side of your double bond. So if you switch 2 groups on the same side of a double bond, you'll get the opposite configuration. That's going to be an important trick that we're also going to use when we talk about chirality. That is all for this lesson. Go ahead and work on the practice. Have a good day.